Okay, we are going to take a look at some properties of Okay, today we are going to look at some properties of polynomials and their graphs and try to make sense of it all. So the first thing we want to look at is the fact that polynomials, whatever size polynomial, pick any polynomial you like, a polynomial is a smooth, continuous curve. So we can see that right here. We can see these graphs that are these nice, smooth, continuous curves. There's no jump discontinuities. There's no holes. There's no kind of weird behavior. It's just you put your pen down and you draw a nice, smooth curve, and that's what polynomials look like. As opposed to over here where we have some discontinuities, we have sharp corners. And this comes in really handy. Those of you going on to calculus are going to love this. The fact that they're smooth and continuous makes the calculus a lot easier to do on polynomials. But here in college algebra, it's also going to give us some insight into the graphs of polynomials as well. So the first thing we want to look at is called the leading coefficient test. And it's really important, and it's summed up by these four outcomes right here. There's four possible outcomes for the end behavior of a polynomial. But what I would recommend is don't memorize these, right? If you understand why these four outcomes occur, then you don't have to memorize stuff. You just think your way through it and you understand what's happening. And it's basically as fast as memorization, but you won't mix it up because you have it memorized and you'll remember how to use it, and then you'll understand the math that you're using. So I'll point out the situations, but again, try to understand them, not just memorize them. So when we talk about end behavior of a polynomial, we're talking about what's going on at the very, very ends of things. So not like around the middle of the graph that we're usually looking at when we're looking at x-intercepts and y-intercepts and maxes and mins and increasing and decreasing and all that kind of behavior. Usually we're looking around the middle of the graph. When we talk about end behavior, we're talking about what's going on not just a little ways away from the middle. We're talking about when you go out, think about massive values for x, right? X passing a million, passing a billion, passing a trillion. An x that is, a number that is 9,000 digits long, right? Just massive, massive numbers. That's what we want to know is what does this polynomial usually end up doing on the ends? And that's what's going to happen. Each end of your polynomial is either going to start shooting up towards infinity or it's going to start dropping down towards negative infinity. That each end has those two outcomes. So that's why we have four possible outcomes, because your left end, the negative end of things, can either go up or down. And the right end, the positive side of things, that side can either go up or down. So if you look at those there's four combinations if you look at those two outcomes from those two situations, and they are categorized here, right? So these first two situations, the important thing is that notice the ends are going opposite directions from each other. This end is shooting down towards negative infinity. This end is shooting up towards positive infinity. Now there's stuff going on in the middle that's important. X-intercepts and maxes and mins and all sorts of stuff, but we don't really care about that because we're talking about end behavior. So at the moment we're only talking about what happens for extremely large values of x and extremely negative values of x, right? So this is what happens. These two situations are what happens for an odd degree polynomial. So if the degree of your polynomial is odd, those two ends are going to go opposite ways from each other. Okay, and I'll explain why in just a moment. And then all you have to do is figure out, well, is it dropping on the left and rising on the right, or is it rising on the left and dropping on the right? Right? Then you just figure that out. Then we have the other situation where the two ends go the same direction. This is what happens when the degree of your polynomial is even. So quadratics, we've graphed a lot of quadratics, right? When you get a parabola every time, well, both ends of the parabola go up or both ends of the parabola go down. You don't see a parabola where they're going the opposite directions from each other. That doesn't happen, right? So, and if you think about it, a quadratic is an even degree polynomial. It's a second degree polynomial. So we're seeing what we would expect. The easiest way to keep these things straight, think of your even, let's jump over to the graph. Can jump over to the graph. Think of just our typical representatives here. Y equals x squared is an even degree polynomial. And look at the two ends are going up together. And we can look at the easy, you could also do a line. I guess you could do a 1-degree polynomial, but we usually think of these polynomials more as like the 3rd-degree polynomials, kind of an early odd polynomial. And what do we have? The two ends of this polynomial are going opposite directions from each other. So we can see that even in very simple examples. This is why it's so easy. You don't have to memorize it. You can just think your way through it. Think about x squared. Oh, x squared, that's a quadratic, so I get a parabola. Oh, and that's where the two ends go together. X cubed, I'm familiar with x cubed. I remember what that looks like in my head, and that's where the two ends are going the opposite direction from each other. So it's very easy to remember. Even polynomials, the two ends go the same direction. Odd polynomials, they go opposite direction. But that still leaves a little bit for us to figure out because, for instance, if you give me a 2nd-degree polynomial, I can say, okay, well, the two ends go the same direction, but do they both go up or do they both go down? And that's the second half of this leading coefficient test is that term in your polynomial, right, the leading coefficient, that term with the highest degree, is that positive or negative? Well, if we see here, in this case, it's positive. Both ends go up. If I throw a negative in front, now they both go down. And that's all there is to it. If you have an even degree polynomial that's the leading coefficient is positive, both ends go up. If that leading coefficient is negative, both ends go down. Okay? And it's the same here for the x cubed, right? This is the orientation we get for positive. A positive leading coefficient, and if I throw a negative in there, look, it just flipped. So it's really easy to play around and remind yourself how this works between even and odd degree, and then the sign of your coefficient is going to tell you whether it's going up or down. Now, why does this occur? Why is this even happening? Well, let's look at this other polynomial, which I just made up here. Just made this thing up. Look, there's lots of terms in it. There's a 4th-degree term, 3rd degree, 2nd degree, 1 degree, 0 degree. Why is it that we only have to look at the leading coefficient in order to understand the end behavior of our polynomial? And the answer is that when you're talking about the end behavior, remember how I prefaced this discussion, you're talking about really large values of x and then really negative values for x. Well, think what's going to happen when you put numbers in here for x, for each of these. Right? Let's say I even take a small number like 10 and I put it in here I put 10 in for x. Okay, that term is 10. Well, what about when I put 10 in the x squared term? Oh, well, that's going to be 100 times 2. That's 200. Well, 200 is way bigger than 10. So we can see that this term has a lot more control over what's going on than this term. What about over here? What about when I plug a 10 into the x cubed? Well, 10 cubed is 1,000, so this term gives us 3,000. That's even way bigger than the 200, right? And then what about here? Well, x to the 4th, that's going to give us 10,000 times 4, 40,000. So that you can see these terms are getting successively bigger. And basically what happens is the biggest term, when you put in extreme values for x, this term with the highest degree becomes so large compared to the other terms, or so small if you're on the negative side of things, that term becomes so powerful it just kind of calls the shots. It gets to be the bully, right? It just says we're doing what I say we're doing, because when this term comes out to 40,000 and this term right here comes out to 10, well, that 10 value isn't going to really affect the 40,000 very much, is it? Even here, when this term was 200, it's not really going to shift our 40,000 very much. And that's the idea. When we're plugging in extremely large or extremely negative values of x, the term that has the highest degree in the polynomial will have so much more control over what's going on because it will be so much bigger or smaller than everything else that everything else kind of becomes irrelevant. Now, remember, I'm talking only about end behavior right now. Of course, the other terms are relevant when we're looking for x-intercepts and maxes and mins, but when we're talking about end behavior, the only one that really matters is that leading term. It tells you the whole end behavior of your polynomial. Okay, so let's use this to think our way through a problem about end behavior. So right here I have a function, y equals negative x to the 5th minus x squared plus 1, and I don't have it graphed, right? For whatever reason, it's not convenient for me to graph it. I just want to think my way through the end behavior so that I know something about the problem that I'm working on. So I want to know about the end behavior of negative x to the 5th minus x squared plus 1. So I look at it and I go, okay, that's a 5th degree polynomial. and the sign on the leading term is negative. So I go, okay, so that's like negative x cubed, right? It's going to have the same behavior as negative x cubed because it has a negative coefficient and an odd degree to the polynomial. So I just think in my head what negative x cubed looks like, and this function down here that we're now concerned about should have the same end behavior. It's going to look different, but what we're going to see is on the left side, this function is going to shoot up towards infinity, and on the right side, it's going to shoot down towards negative infinity. So let's see. Yep, we're getting that same behavior. Now it looks different, and we don't really care about what's going on in the middle for the moment, but we can see on the left, they're both shooting up towards they're both shooting up towards positive infinity, and over here on the right, they're both shooting down towards negative infinity. So we were able to figure out that end behavior very quickly without having to crunch any numbers or write anything down or without having to do any graphing. I could just identify that right away. Okay, the next property that we want to look at is called multiplicity. Now I notice that a lot of students kind of don't really pay attention to multiplicity, and you can do most problems without worrying about multiplicity. But what I'll tell you is it can make your work a lot easier. If you pay attention to multiplicities, if you understand how they work, there's a lot of times when you can cut out a lot of the work that you have to do for a problem because you just think your way through the problem using multiplicities. So let's take a look at what this means. So when we talk about multiplicity, what we're really talking about is the power that occurs on a certain factor in a polynomial. So is that factor just occurring once? Is that factor being squared? Is it being cubed? Is it being raised to the 4th, to the 6th, to the 11th? What is the power on that factor? And if it is odd, then we call it odd multiplicity. If it's even, we call it even multiplicity. And here's why we care. If r is a 0 of even multiplicity, then the graph touches the x-axis and turns around at r. It doesn't cross the x-axis. So think of x squared, think of a parabola, where your parabola comes down, touches the axis, and then it goes back up, right? Just like an x squared, y equals x squared. That's kind of your base example for even multiplicity. We'll look at it in the graph in just a minute. If r is a 0 of odd multiplicity, then the graph crosses the x-axis at r, okay? So let's take a look at that. So we can see that with our two base examples that we've been using, x squared and x cubed, right? The most basic even multiplicity problem you can come up with, y equals x squared, and here we go, right? This is, you could think of it as x minus 0 being squared, right? So if you want to think of it as a factor, right? We just write it as x squared, but you could think of it as x minus 0 squared. That factor that corresponds to the 0 of 0 has even multiplicity, so that, according to what we just read, means that it comes down, it touches right at that 0, and it goes back up. It does not cross the x-axis, as opposed to x cubed, which does cross the x-axis, right? In this case, our factor is being cubed, so odd multiplicity, and when it has its x-intercept, it actually crosses and goes to the other side of the x-axis. Okay, so we can see this with ones where the factors are a little bit more obvious. Here I have an x minus 2 squared. We know that's just a parabola shifted over 2 units. And there it is. It's multiplicity 2, so it's even multiplicity. And it's just sitting right on the x-axis. It doesn't cross it. It comes down, touches it, and goes back up, as opposed to this one here, now x minus 2 cubed, that's odd multiplicity, and notice how it's crossing the x-axis. So say I've got y equals x minus 2 squared, and I want to multiply by the factor x plus 3 cubed, and we graph that, and sure enough, if we look over here, this is the 0 corresponding to x minus 2, because it's x equals 2, and sure enough, that has an even power over here, and our function comes down, touches the axis, and goes back up. Whereas our factor over here, x plus 3, that corresponds to an intercept of negative 3, that has a power 3 on it, so it's odd, and that one is crossing the x-axis. That's really what multiplicity is getting at. And by knowing those, you can sometimes double the work you've already done and go, oh, well, I just found the 2 zeros instead of just finding them one at a time. multiplicities can be very convenient. They can save you a lot of work. Next thing we're going to look at is the intermediate value theorem, and luckily the intermediate value theorem, besides being really helpful, is actually pretty straightforward to understand. It basically says that if you have a continuous function, right? So think about that. We have continuous function. There's no jumps, there's no holes, there's no anything like that. Well, if you have part of your graph where there's a point where your x value corresponds to a negative y value. So that's what we see in this picture. The a value is giving us a negative y value, right? And then sometime later in that graph, you have an x value that's corresponding to a positive y value. So you have one value that's occurring below the x-axis. You have one value that's occurring above the x-axis. And we've already stated that we're dealing with a continuous function, right? We're talking specifically about polynomials, and polynomials are continuous, but this is true for any continuous function, is that if you have a continuous function that connects those 2 points on the graph, one having a negative y value to one having a positive y value, then ask yourself, what must happen along the way? For a continuous function, like to think about drawing it, you're going to draw a point or a curve from that negative point with the negative y value up to the positive y value. What are you going to have to do somewhere in between while you're drawing that for a continuous function? Well, somewhere along the way, you're going to get an x-intercept. You're going to have to cross that x-axis to go from negative territory to positive territory. Somewhere along the way, you have to cross the border, right? So you're going to end up with this value here, where here is where we crossed from negative territory to positive territory, and that's all the intermediate value theorem says. Now, it relies on it being a continuous function, right? When we start getting into non-continuous functions, then this doesn't hold. But anytime you have a continuous function, if you have a positive value and a negative y value, then you know that somewhere in between there has to be an x-intercept. And that's helpful because a lot of times that's what we're looking for, right? We're looking for zeros of functions. We're looking for solutions to equations. So, those are the things that we're looking for. And so having tools to find them and narrow down where they are can be very helpful.